Surficial processes. The Earth's external heat engine. When tectonic forces shove a portion of the Earth's crust above sea level, rocks are exposed to the atmosphere. The Earth's external heat engine, driven by solar power and gravity, then comes into play. Our weather patterns are largely a product of this heat engine. Hot air rises near the equator, for instance, and sinks in cold regions nearer the poles. Solar heating of the air creates wind. Ocean waves, in turn, are produced by wind. When moist air cools, it rains or snows. Rainfall on hillsides flows down slopes and into streams. Streams flow to lakes or seas. Glaciers form where there is abundant snowfall at high elevations and colder temperatures, and they flow downhill due to gravity. Where moving water, ice or wind loosens and removes material, erosion is taking place. Streams flowing toward oceans remove some of the land over which they run. Crashing waves carve back a coastline. Glaciers grind and carry away underlying rock as they move. In each case, rock originally raised by the Earth's internal processes is worn down by surface processes. Rocks formed at high temperature and under high pressure deep within the Earth and pushed upward by tectonic forces are unstable in their new environment. Air and water tend to cause the once deep-seated rocks to break down and form new materials. The new materials, stable under conditions at the Earth's surface, are said to be in equilibrium, that is, adjusted to the physical and chemical conditions of their environment so that they do not change or alter with time. For example, much of an igneous rock, such as granite, that formed at a high temperature tends to break down chemically to clay. Clay is in equilibrium, that is to say, it is stable, at the Earth's surface. The product of the breakdown of rock is sediment, loose material. Sediment may be transported by an agent of erosion, such as running water in a stream. Sediment is deposited when the transporting agent loses its carrying power. For example, when a river slows down as it meets the sea, the sand being transported by the stream is deposited as a layer of sediment. In time, a layer of sediment deposited on the seafloor becomes buried under another layer. This process may continue burying our original layer progressively deeper. The pressure from overlying layers compresses the sediment, helping to consolidate the loose material. With the cementation of the loose particles, the sediment becomes lithified, cemented, or otherwise consolidated into a sedimentary rock. Geologic time. We have mentioned the great amount of time required for geological processes. As humans, we think in units of time related to personal experience, seconds, hours, years, and a human lifetime. It stretches our imagination to contemplate ancient history that involves 1,000 or 2,000 years. Geology involves vastly greater amounts of time, which is often referred to as deep time. To be sure, some geological processes occur quickly, such as a great landslide or a volcanic eruption. These events occur when stored energy, like the energy stored in a car battery, sometimes stored for centuries, is suddenly released. Most geological processes, however, are slow but relentless, reflecting the pace at which the heat engines work. It is unlikely that a hill will visibly change in shape or height during your lifetime, unless through human activity. However, in a geologic time frame, the hill probably is eroding away quite rapidly. Rapidly, to a geologist, may mean that within a few million years, the hill will be reduced nearly to a plain. Similarly, in the geologically recent past of several million years ago, a sea may have existed where the hill is now. Some processes are regarded by geologists as fast, if they are begun and completed within a million years. The rate of plate motion is relatively fast. If new magma erupts and solidifies along a mid-oceanic ridge, we can easily calculate how long it will take that igneous rock to move 1,000 kilometers away from the spreading center. At the rate of 1 centimeter per year, it will take 100 million years for the presently forming part of the crust to travel the 1,000 kilometers.